2.3, inverse trigonometric functions. We're going to pick up where we left off last time, where we were taking a look at the inverse sine and inverse cosine last time. Let me just remind you a couple of the things about the way those work. So the first thing is that we have to have what are called one-to-one functions. One-to-one functions have to pass the horizontal line test, which means that it can't cross the graph in more than one location if I draw a horizontal line. The problem is that every single one of our trig functions fails this test royally. I mean, like on steroids, like it's bad. So in order to actually be able to use inverse functions for trigonometry, we have to restrict our sort of viewing window. And so we talked about for sine and for cosine what that would look like. So for sine, our restricted window is from negative pi over 2 to pi over 2. And for cosine, our restricted window is from 0 to pi. And when we took a look at this, we also specified which quadrants this was in terms of the unit circle. So for sine, this is in quadrants 1 and 4. And then for cosine, this is in quadrants 1 and 2. So cosine's the weird one here, right? It's the even function, but it's sort of the odd man out. Everything else has dealt with negative pi over 2 to pi over 2. And in particular, we saw it happen again on tangent. So tangent was quadrant 1 and 4 as well. So cosine is the one that's weird, it's 1 and 2. So we're going to take a look then at what happens when we look at the other three inverse functions. So inverse cotangent is our next one. So we're not going to go in huge amount of detail like we did on the others as to how this is sort of set up, because these are reciprocal functions, which means a lot of the things they get almost for free. Inverse cotangent doesn't pair up exactly with tangent, and that is a little bit different. Now, the reason it doesn't is because if you'll remember the graph of tangent, and let me just sketch it in here, at least, hang on, one of the cycles of it. The inverse, or so not inverse, but the cotangent graph has asymptotes that go from the y-axis over here to pi, and it's a decreasing graph that looks something like this. Okay, nod your head if that looks familiar. Y'all just took a quiz on some of those things, right? So this one is actually also in quadrant 1 and 2, which is like cosine. Even it's cotangent, right? But it doesn't match up with tangent because its asymptotes occur in different locations. So it is in quadrants 1 and 2, like cosine. So now we've got two of them in quadrants 1 and 2, and we've got two of them in quadrants 4 and 1, right? 1 and 4. The other two go with their reciprocal pair. So secant is actually taking a look at the inverse, the inverse secant is going along with cosine, right? Secant and cosine go together. And if you take a look, this down here is in quadrants 1 and quadrant 2. Notice there's a break between them. It doesn't have a value, right, when you are actually at pi over 2. And if you'll remember, the reason why is because there's an asymptote there. Okay, so if there's an asymptote, we don't have an actual value of our function. And the domain and the range switch. So previously, the domain would have been 0 to pi halves to pi, and now that's the range. And then the range previously was negative infinity to negative 1, and we do this jump right over the cosine graph. We pick up from 1 to infinity, and that's now our range, our domain, which was previously our range. And then cosecant pairs up with sine. So cosecant with sine is taking a look at quadrant 4 and quadrant 1, just like sine did. And again, it breaks at 0 because there's an asymptote at 0. So our graphs look something like this. I already drew the first one on the previous screen. Let me look at a brief sketch for secant first. So for secant, the graph of cosine, if you'll remember, it looks like this. Whoops, sorry, it changed my. And we restricted looking at this picture for cosine so that it stopped right here. Right, that's kind of where we restricted our picture for cosine. And if you take a look at the reciprocal function for secant at that location, we have this branch opening upward. We have an asymptote here, and then we have a branch opening downward. And it is the yellow right there, right? The yellow, it is 1-to-1. on those pieces. But if you continue either of those pieces in either direction, left or right, you will start repeating y values and it won't be. For example, if I continued this branch down, all of a sudden now I draw a horizontal line, it crosses it in two places. Okay, so this restriction for quadrants 1 and 2 makes perfect sense in terms of that visual. And then if we look at cosecant, we're going to have the same sort of thing going on. Our sine graph is going to go from, oh, that's a little bit low. Well, we'll just make it small. How about the same green? It looked like this for sine. That's not very good. How about that one? Right? So it went from negative pi over 2 to pi over 2. And if we draw the corresponding pieces for cosecant, they will look like this. And then I've got an asymptote at the y-axis like this. So again, we get enough of it to get all the pieces without any overlapping y values. So it might not be a bad idea. I'm going to flip back a screen to just put a little bit of a chart in place. I don't have this in your notes anywhere, but I think it might be helpful to remember which ones are in quadrant 1 and quadrant 2, and which ones are in quadrant 1 and quadrant 4. So somebody give me a quadrant 1, quadrant 2. Well, actually, I've got one on the screen here. Let's just put this one here. Cotangent. Cotangent, inverse cotangent rather, but is in quadrants 1 and 2. Something else that's in quadrant 1 and 2. Cosine. Yep. So inverse cosine is in quadrant 1 and 2. There's one more in quadrant 1 and 2. Secant. Yep, it's secant. Okay, so all the rest of them are in quadrant 1 and 4. So we've got inverse tangent. So those are the ones that are sort of odd because their cofunction does not go with them, right? So the cotangent and the tangent, those two do not go together. I should say the reciprocal function does not go with them. And then I've got sine. Okay, so my inverse sine is in quadrants 1 and 4, and my inverse cosecant is in quadrants 1 and 4. So all of these trig functions are in those particular quadrants when I'm looking at values. And so what does that mean? Well, it means that the answer needs to be within those intervals. So if I'm finding an inverse cotangent value, whatever value I get better be an angle measure in quadrant 1 or quadrant 2. So if you give me an angle measure that's outside of that quadrant, you're automatically in the wrong place. Okay? So this tells you which quadrant you should be finding an answer in from a unit circle's perspective. Okay, so let's take a look at a couple of examples then with these additional three trig functions that we've added on since last time. So it wants us to find the value of each expression, the inverse cotangent of 1. So as we take a look at this, what you'll remember from last time is we're going to set this equal to an angle measure. So I'm going to call it theta. You can call it something else if you want. And I'm going to rewrite it. And when I rewrite it, what happens is that I sort of move the cotangent in this case to the other side. So this is the cotangent of theta on the right. And again, the reason that that's happening is because I'm sort of operating cotangent on an inverse cotangent here, right? And these cotangent inverse cotangents are canceling. That's what's happening there. So in terms of your unit circle, you're trying to think of where is my cotangent value equal to 1? Now, if you'll remember, cotangent and tangent are the ones that you cannot just read straight off of your unit circle, right? So cotangent is x over y. So in order for them to actually have a value of 1 when I divide them, it must mean that x and y are the same. Does that make sense? In order for me to get a 1, I've got to have an x and a y value that are the same. I also have to have a value that's positive, right? This is positive. So if it's positive, well, let's just say, we already wrote this down before, but cotangent's in quadrants 1 and quadrant 2. So which of these quadrants is going to have positive cotangent values? Quadrant 1, right? Quadrant 1 is where all of my positive values lie, okay? Quadrant 1. So I'm supposed to be in quadrant 1, and I need to be in quadrant 1 where the x and the y values are the same. What angle measure is it where that happens? In radians, always radians. That is at pi over 4. Okay? So if you remember, at pi over 4 right here, we're at square root 2 over 2, square root 2 over 2. Okay, so when I divide them by each other, I end up getting the value 1. My answer then for this question is that I am at theta equals pi over 4. Yep, you're just finding the exact value, which is finding the angle measure. So anytime you're asked to find an inverse trig function, you're being asked to find the angle measure that gives you that value for that trig function. That's what you're being asked to do. So while cotangent and tangent have this sort of nuance that we have to remember there's a ratio, the same is actually true when we're looking at secant and cosecant. They aren't exactly ratios. I mean, they are. They're not a very exciting ratio because you've got one on top. But they do end up creating values that are not directly on my unit circle. For example, 2 square root of 3 over 3 is not a value on my unit circle, right? It's not an x value or a y value. So let's take a look at how this would work. So we're going to put this in terms of theta. And we're going to change it so that this is now negative 2 square root 3 over 3 is equal to the secant of theta. Now, there's more than one way to sort of reason and think through this, but I'm going to show you one option that I think could be helpful. It's not real pretty to look at secant, but looking at cosine is very nice on a unit circle because it's simply the x value. So I would like to change this into an expression that's an equivalent expression about cosine. So if the secant is 2 square root of 3 over 3, negative, then the cosine would be the reciprocal, which is 3 over 2 square root 3. Just flip it upside down, right? These are reciprocals of each other. Now, again, I don't have that value exactly on my unit circle, but I can adjust it so that I can see it pretty quick. If I take this and I rationalize the denominator like that, I will get 3 square root of 3 times 3. And check out what happens to the 3's. They cancel, right? So I'm back to having negative square root 3 over 2 when I simplify that. Now, some of you might have looked at that and said, I knew that's what that was to begin with. Fantastic. If that's you, that's great. Write it down and you're good to go. Don't show the pieces in between. That's fine. But it's a little bit tricky to see the first few times you work with it. So if you need to do it, write it out. Flip it around. Rationalize it. This value, negative square root 3 over 2, is an x value on the unit circle. Now, what quadrants am I in for secant? It's always quadrant 1 and something else. Quadrant 1 and 2, right? For secant. So this is a secant value that's negative. Which quadrant is going to have my negative secant values? 2, right? Quadrant 1 is always the positive. Quadrant 2 or 4, whichever one it is always going to be the negatives. So it's quadrant 2. So I need to be thinking quadrant 2, x value that is negative square root 3 over 2, right? So I'm roughly speaking over here or over here. It's one of those two because those are the ones that give me square root 3 over 2's. Which one gives me the x value that's square root 3 over 2? The one that's closer to the y-axis or the one that's closer to the x-axis? The x-axis. It's this one right here. What is that angle measure? 5 pi over 6. You got it. So this is equal to cosine theta. Let me just kind of fill in the pieces I left off. So what we just found out then is that the theta value is 5 pi over 6. Yep, Deacon.
I'm sorry, but how are you figuring out the quadrants?
You mean that it's quadrant 1 and 2 or that it's quadrant 2 specifically?
Quadrant 1 and 2.
Quadrant 1 and 2. Okay, so over here when we were taking a look back on Friday, one more back I think, that's the one, we drew a graph of cosine, okay, and we restricted it to a certain window because we have to have a one-to-one graph. The window that this restricts to always is from 0 to pi. And 0 to pi, when these are my values, on a unit circle are in quadrant 1, right, on the positive x-axis, all the way over to quadrant 2 on the negative x-axis. So that's why it's quadrants 1 and 2.
Yeah.
Okay, and we can do that for all the trig functions. Cosines just happens to be 1 and 2. And that's why I wanted to put this chart here kind of into your notes for you guys to be able to refer back to. So that you don't always have to be thinking back through the exact graph every time, especially at the beginning here where you're just working with like, which one was switch again, which one was switch again. This is one place that you could look and you could have them all kind of in the same spot. Okay? All right, we're going to take a look then at what are called composite functions. So this is in your notes printed out already. You don't have to write any of this down if you've printed your notes. This actually talks about when you take the inverse trig function of the trig function or an inverse function generally of a function. and what happens. So you'll see that I've sort of been using this fact already. That when I do the inverse sine of the sine, I get back x. When I do the sine of the inverse sine, I get back x, right? So this is sort of like, well, when you multiply by 5 and then you divide by 5, you don't change anything, right? This is the same idea. But it actually only works when you're in the right locations, right? Like you have to be in quadrants 1 and 4 for this to work for sine. You have to be in quadrants 1 and 2 for this to work for cosine. And you have to be in 1 and 4 for it to work for tangent. They have to be in the right locations. Because if they're not in the right locations, then you actually can end up changing locations. So let's take a look and you can see what that looks like when we're actually in the wrong location, okay, versus the right location. So here's an example of one. In general, what we would say is we should be able to cancel out the cosine inverse and the cosine, and the answer should be 4 pi over 5. Like that's what we would expect to happen. But that will only happen if we are in the correct quadrant. So we need to figure out, because 4 pi over 5 is not one of our unit circle angle measures, right? I mean, it's just not. So we need to figure out where we are in terms of what quadrant we're in when we're at 4 pi over 5. So where is 4 pi over 5 in terms of a quadrant? Oh, sorry. Let me write this down. So 4 pi over 5 is in quadrant 2. So how do you know that? You're right. How do you know?
It's more than pi over 2, but it's less than pi.
Perfect. Did you guys catch that? This is bigger than 1/2 of a pi. It's bigger than pi over 2, but it's smaller than pi. So this is in quadrant 2. Well, cosine, is cosine in quadrant 2? Is that where we're defined for cosine? It's that chart. Cosine is quadrant 1 and quadrant what? Is it 2 or 4? 2. Right? This works. This is in quadrant 1 or 2, specifically in quadrant 2. So these actually will reduce or cancel one another out. They're inverses of one another. 4 pi over 5 ends up being my answer. And the reason is because that value 4 pi over 5 is between 0, specifically between 0 and pi. I know we said it's between pi over 2 and pi. But it's between 0 and pi, or we can say it's in quadrant 1 or quadrant 2, right? That's what we're looking for, which is where the inverse cosine is defined. It works because I'm in the right spot to start with, okay? That's why it works. Now, we're not always in the right quadrant to start with. So now we got to figure out when it happens that we're not in the right quadrant to start with, what do we do? Because that's what's going to happen on my next one. So let's take a look at the next one. The next one says I've got the sine of 2.57. Now that's not very friendly because it doesn't even have pi in it for us to reference things very well, admittedly. But we can work with it. So if we're thinking unit circle, right? So here's 0. This is pi over 2. And this one's pi. And this one's negative pi over 2 if I go backwards, because I've got to figure out where I am in terms of my spaces. Pi over 2, what's pi? Let me write that one first. About 3.14, right? Everybody good with that? Approximately. So what would pi over 2 be approximately? It's about 1.57. Okay, so these equals should really say they're not exact, but they're giving us some sort of perspective. So if I've got angle measures that are 1.57 and 3.14, and my angle measure is at 2.57, what quadrant am I in? I'm in quadrant 2. It's over here somewhere. I don't know where, but somewhere. It's somewhere between 1.5 and 3.1. Right? It's somewhere over there. So this is in quadrant 2. Why is that a problem? I was in quadrant 2 last time and it wasn't a problem. Exactly. It's supposed to be in quadrants 1 and 4 for sine, right? Okay, so put yourself sort of like an asterisk, a star. This is a problem. And the reason is because inverse sine is defined in quadrants 1 and quadrant 4. And this is in quadrant 2, not 3, 2. Okay, so we have to do something. Like, we got a little work to do. We don't just get to cancel out the inverse sine and say the answer is 2.57. It's not. It just isn't. That's not the right value anymore. Okay? So we need to figure out what we do have to do to get the right value for the inverse sine. So taking a look at this, we're going to go back to something we've done before that you didn't see real clearly why we needed it, maybe. But we talked about something called reference angles. Do you remember that? So our reference angle references where we are in respect to the x or the y-axis. Okay, specifically the x-axis is what we look at. So this measure right here is the reference angle. That's what it would be. So it takes our angle and it drops it down to the nearest x-axis and it finds that angle measure. That's what a reference angle does. So what would I do to find the reference angle? I'll show you why we need it, but just what would I do to find the reference angle for my 2.57 angle measure? Subtract it from pi, right? So I would take pi, because that's all the way over to the negative x-axis, and I would subtract off the 2.57 that I'm at above. Now we can get an approximation for that. We're going to use it both in its accurate form, which is pi minus 2.57, but we can do an approximation as well to reference it for us. So what is that value if I do pi minus 2.57? What is that approximately? What was it? 0.57. Okay, it's 0.57. Okay, so what I need to do is I need to reflect this image back into either quadrant 1 or quadrant 2, wherever it is that I'm actually supposed to be to have that same sine value. So which quadrant am I in where I have the same sine value, right? There's like the xy here, right? There's an xy. Sine's y. Which quadrant will have the same y value as this point? Quadrant 1. Okay, over here, there's a measure right here that has the same y value as we have over here. Like these match, right? But in order for them to match, what it means is that this measure is the same as the measure over here that we said was 0.57. So this angle measure and this angle measure have to match in order for those y values to be the same. That's where that reference angle is coming from. So what's it matter? Well, what we're actually doing is we're reflecting back into the quadrant that we're supposed to be in. The quadrant we're supposed to be in order to be able to do this sort of inverses the way we're supposed to is supposed to be quadrant 1, because that's going to give me a sine value that's exactly the same thing. So here's the way that this looks. I'm kind of all over my board. I apologize for that. So 2.57 is not less than or equal to pi over 2. We established that, right? It's more than pi over 2. But the sine of 2.57 is the same as the sine of pi minus 2.57. Okay, which we also said was 0.57 here, if you want to prefer that. So the inverse sine of the sine of 2.57 is actually that pi minus 2.57, or approximately 0.57 that we saw. This is the exact value of this trig function. 0.57 would be an approximation if you were asked to approximate. Now check it out. Grab your calculator if you have it with you. If you don't, that's fine. It's not a big deal, but you can actually check to make sure that this makes sense. I would like for you to type in, make sure you're in radian mode, right? Type in inverse sine. If you're not sure where that is, it's usually under the sine button, and you usually have to press like a second key or a function key first, and it'll put that inverse cosine or inverse sine, whatever it is you're working with. So if you type inverse sine, and then you do a parenthesis if it requires it, and then you type sine, and then you type in 2.57, it should give you a decimal approximation of 0.57. Did it work? Emily says yes. We got a couple yeses over here as well. Great. Okay, so can you verify this? Sure. That's fantastic. You're going to have to show me some work, though, because I don't really care that your calculator knew how to do it. I care that your calculator can verify it. That's great. But I need you to understand why it's happening. It's not just magically disappearing the 2, because it kind of looks like it, doesn't it? It just subtracted 2 off. It didn't subtract 2 off at all. Like, that is not what happened, but it kind of looks like it. So we want to be careful that we understand why it's changing. All right, let's do another one. A couple more, actually, of these variety. Tangent of the inverse tangent of 4. Okay, so this one right here is our value, our 4. So tangent of inverse tangent, remember what the values were on that one. So let me actually pull up our page that had that on there. Is it here? No, it's that one. That's cotangent. Sorry. Last time. How about here? There we go. All right, so our inverse tangent says that its domain is negative infinity to infinity, right? And that makes sense when we look at the tangent's range. It went from negative infinity to infinity. Agreed? So what that's telling you is that you can have any input value in here at all, any value that goes into inverse tangent, and everything's going to hold. Okay? So when we're taking a look at this new one that we're on, right here, this value is fine. There's nothing wrong with 4, right? We had a problem over here on the last example with 2.57. That was a problem. It's not a problem for the number 4, because for tangent and for cotangent, we have infinitely every possibility for an input value. So this works just fine. So because negative infinity is less than 4 is less than infinity, or you can say because the domain is all real numbers, or because I can have any input for x I want for tangent. Any of those are fine, right? We know that the tangent of the inverse tangents are going to cancel. For 4 is going to just give me back 4, right? These will cancel out because the input's valid. Last one, the input wasn't valid. That's why we had to work with it more. The one before that, the input was valid. It was great. Canceled them out and we're good to go. So the work to be done is checking the input. And then if the input doesn't work, we have to see what we can do next. Let's try one more. Now this one has an input of 4 as well, but it's not tangent, it's sine. And that makes a difference. What inputs are we allowed to have on our sine function? Go back to the very front page that we did last time. What are my domain values for inverse sine? Yep, -1 to 1. What's that tell you about 4? That doesn't work, right? And it can't just be adjusted the way that we adjusted that 2.57 before. So I'd like for you to take a look and compare this problem, number 8, with our problem number 6, problem number 6 from before. I want you to look not at the 4 and the 2.57, but I want you to look at the order of the trig functions. What do you notice about the order of the trig functions from 6 to 8? The location of the inverse is in a different spot. Do you guys see that? Okay, so this is this one. Let me write the other one just so that I have them on the same screen. Problem number 6 said the following. I didn't mean to put it in green, but I guess I will now. It said, inverse sine of the sine of 2.57. Okay, so the inverse sine is in a different location on these two problems. Are y'all tracking with me? It matters. Okay, so on the first one that we did, number 6, the one that's here at the below, this right here is an angle measure. Okay, so my angle measures repeat. They go around the circle. I can add and subtract pies and 2 pies and different things to put and be in different locations, all that kind of stuff. This number 4 is not an angle measure. This is an output value. So think about your output values, your y values on the unit circle. Or think about the graph of sine itself, where it bounces up and down, right? Where does it bounce up and down between? 1 and -1. Unless I have an amplitude difference, like we talked about last time. Emily asked about some amplitude stuff, and I was like, we don't have to really worry about that, right? So unless I have an amplitude issue, which that's not what's happening, right? I don't have a number in front kind of thing going on. This should be bouncing up and down between 1 and -1. It never gets to 4. It's not possible. So we're going to jot that down in a more like formal way. The inverse sine of 4 is not defined. Because 4 is not on the interval -1 to 1. So this one is not possible. Right, as in there's no solution. It can't be done. Yes?
Could it be done if it was the inverse was on the outside?
Sure.
Label it as-
Absolutely. Yeah, if the inverse was on the outside, it would turn it into the problem number 6 that we did before. We'd be looking at where we are in the unit circle. In that case, we'd be in quadrant 3, and we'd have to reflect the correct quadrant and look at reference angles and so forth. Yeah, absolutely. Okay. The same thing is going to happen on the next set. The directions look a little bit different, so let's take a look together. It says use the properties of inverse functions, that f of f inverse is equal to x of x is equal to x for all x in the domain of f inverse, and same for the other, as well as the definitions of inverse functions to find the exact value of each expression. And it tells you on these, right, if possible. We just saw one that was not possible. Okay. So let's take a look at this. We need to figure out where we are, because the inverse cotangent's on the inside, right? So in terms of inverse cotangent, what are my valid inputs for that? What am I allowed to have? Can you flip back to that screen, or shall I? Do you guys want me to flip back there? Let's see if I can find it.
Negative infinity.
Yes, you got it. It's this one right here. It's negative infinity to infinity. That's my domain. So this is very friendly, right? I mean, at least in the sense of it's okay. We can make that work. Negative pi, it works. So negative pi is on that interval. So negative pi is between negative infinity and infinity. So we are actually able to cancel these out. So the cotangent of the inverse cotangent of negative pi is just negative pi. And we're done. Because we checked it was on the domain. It was, so we're good. Let's try another one. And then we're going to mix things up a little bit with some composite functions. 7 pi over 4. Now this is a secant value, right? So notice again, kind of like what Keith pointed out and what we talked about, where the location is of the inverse matters. The inverse on this one's on the outside. So this one is an angle measure. This is the first angle measure we've had in about 4 problems, right? Where are we when we are at 7 pi over 4? We're in quadrant what? We're in quadrant 4. We're down here. Okay, is everybody good with that? We're in quadrant 4, but we're in quadrant 4 from sort of a funny perspective because on our other quadrant 4s, we're going backwards and this one's going forward. So that's okay. But we're in quadrant 4. We're down here. Okay, where are we supposed to be when we're working with secant? Yep, we're supposed to be in quadrants 1 and 2 for secant, right? So am I in the right quadrant? Nope, I'm not. So where will I reflect? Will I reflect into quadrant 1 or will I reflect into quadrant 2 in order to be the same secant value? Of 1. We're going to reflect up into quadrant 1. Secant values relates to x. The x values are positive when I'm on the right-hand side of my graph. So I'll reflect back up to still be on the positive side of the graph. So I need to be up here instead. What is the corresponding angle measure right there that would be in the same location as my x value? It's pi over 4. And the reason that's happening is the angle is negative pi over 4, right? Well, the angle is negative pi over 4. The reference angle would be pi over 4. So it's reflecting in the same spaces. So secant, the inverse secant rather, of the secant of 7 pi over 4 is the same as the inverse secant of the secant of pi over 4. Those are the same location. Well, they're the same secant value. These are not, I'm not saying that the pi over 4 and the 7 pi over 4 are the same value, but the secant of them is. And now I'm in the correct quadrant, so I'm able to cancel out my secant and my inverse secant, and I get back pi over 4. And the reason is this is because they have the same, technically it's 1 over x, not just x, but 1 over x value in quadrant 1 and in quadrant 4. That's why that's happening. I have the same x value, so I have the same reciprocal 1 over x value in those quadrants. Okay. Let's shift gears a little bit and tell me, what do you notice is different about problem number 11? Two different trig functions, right? I've got sine and I've got inverse tangent, not sine and inverse sine. Are you good with me? Okay. So let me show you how these work, and they'll be back to triangles. Some of you are like, oh man, I was hoping we get back to triangles. And some of you are like, man, I didn't ever want to see a triangle again. It's okay. We're going to all do it together. Okay, it's going to be back to a triangle. So we're going to start with what's inside, just like you would with any grouping symbol. We'll start what's inside. So what's inside is an angle measure. This is the inverse tangent of 7 over 24. It equals an angle. And if I rewrite it, just like we've been doing on the others, this is 7 over 24 equals the tangent of theta. Okay, already good so far with the rewrite. And I'm not dealing with the sign on the outside yet at all. That's a secondary issue. I want to draw a triangle that reflects, a right triangle that reflects a tangent that is 7 and 24 in the correct locations. So we're going to draw our triangle. That's a terrible triangle actually, but we're going to go with it anyway. Pretend for a moment that that's supposed to be a right angle and everything looks good. I probably could have done a better job freehand, but that's great. Here's my angle theta. What is tangent in a triangle? Opposite over adjacent. So opposite would be the 7. So that is opposite my angle, and adjacent would be my 24. Definitely nothing drawn to scale, and I don't care, right? How can I find this third side? Yep, Pythagorean theorem. A squared plus b squared equals c squared. So 7 squared plus 24 squared equals c squared. Remember, c is always opposite the 90-degree angle. It's not c because I don't know it. It's c because it's opposite the 90. This is 49, and I have 576 written down, so that's probably correct, which is 625. What is my square root of 625? 25. And you might have known that. This is a Pythagorean triple. It means it has all the interval, all of the sides are in integers is what it means. So this one's 25. Okay. The work is done. Now you get the last part for free. You ready for it? Okay, you did the work, you found the triangle, you did the Pythagorean theorem, found the third side, all the good stuff. Now you come back over here to sine, and you look at the triangle and you say, in this triangle, what's the sine value? 7 over 25. That last step is the easy step. It's just reading off of your triangle. Yep, Keith.
How did you know that was the theta angle?
You can put the theta wherever you'd like. It doesn't matter. It just needs to not be the right angle because it's always the acute angle.
Okay.
Yep.
I didn't know if you use like the unit circle or like.
You don't have to. No, this was like this. When we were setting things up like this, it predated the unit circle. There's nothing special about the unit circle drawing this. So I usually put it as a base angle, but like on the bottom, opening upwards, but it doesn't have to be. You could have drawn it on the top. It would have been just fine. So our sine value of this angle measure then is 7 over 25. And that's our answer. Okay, let's try another one. I think I've got another one. I got a couple more. Okay, same process. I start with what's inside. I set it up so that it is equal to theta, like that. And I rewrite so that I have the cosine of theta on the other side. Or if that bothers you, write it as, good grief, cosine of theta equals 1/2 so that it's written left to right with the angle on the left. It doesn't matter. Either way, I'm drawing a triangle. And Keith, you'll see me put the angle of theta at the bottom because that's just my default, but you can put it either location. Cosine, what is cosine in terms of triangle? Adjacent over hypotenuse. So adjacent would be the one down here at the bottom on the way I've drawn mine. And the hypotenuse would be the number 2 right here. Okay, are we good? How am I going to find the third side? Pythagorean theorem. So let me call it B so that I have a reference for it. So this would be a 1 squared and a B squared, right? Not because I don't know it, but because it's a side of a triangle, the leg, yes.
Would this be 1, 2 squared and 3 triangle?
It will. You're going to see that happen. And if you notice that in advance, that's great. Yeah, so hold tight. You're correct. So a 2 squared here. So I have 1 plus B squared equals 4. B squared is 3. And just like Deacon noticed, this actually is one of our unit circle value triangles. Did it have to be? No, but it happened to be, and that's okay. So this one is square root 3 right here. Okay, we've done all the work. The last step is to read the tangent value off of the work that we've done. What is the tangent value of this angle that we've created? It is square root 3 over 1, or feel free to just write it as square root 3. Okay, let me do one more, and then we'll table this for today. We'll come back to it next time and discuss adjusting our schedule, which is fine. Cotangent of inverse cosecant of 8. Okay, so starting here at the inside with the parentheses, I have the cosecant inverse of 8 equals theta. And I rewrite 8 is the cosecant of theta, right? We did this before. Well, cosecant is the same as 1 over sine. So I have a tendency to say I don't like seeing any of the trig functions that don't have SOHCAHTOA with them. That's my default. And so I will rewrite sine as 1 over 8 and do the reciprocal. That's how I will always think about it. And then I go to my triangle. And I put my angle theta in there, and I'm dealing with sine. Sine is what? Opposite over hypotenuse. This is not a familiar triangle to us. The last two could have been, depending on your perspective. We'll call this side A. So this is a squared plus 1 squared equals 8 squared. A squared plus 1 equals 64. A squared 63, and lo and behold, A is a very awkward square root 63. But we've done all the work. Now we read cotangent off of this. What is cotangent in terms of a circle, or in terms of a triangle? Yeah, it's adjacent over opposite, right? So the cotangent that we're working with now, I'm going to write this one down because it's the adjacent is square root 63. The opposite is 1. So this is simply square root 63. Okay, you are welcome to start your homework. We will not have it finished because there's 2 more questions that I have as examples that we need to get to in order to finish up the very end of the assignment. You'll know when you get to them, because what's the primary difference between this and the previous slide? There's no number inside. There's a variable inside, right? That's going to be the last thing we're going to do in this section. We'll pick up with that on Wednesday.